Good evening and welcome to this second live interactive session of this NPTEL course, Advanced Transition Metal Organometallic Chemistry. So this is the last session which we have prior to the start of your exam, which will be in the next week. So if you have any questions or queries or any doubts, we'll try to clear it out in this session. And the format is that you're going to be sending us your queries and questions through text messages. The text box is located in the bottom right hand side of your screen. So please text us your questions and we will answer them. I hope by now you have attended most of the lectures and I wish and I also sincerely hope that you have found this course informative, enjoyable, and also it has helped you uh, garner interest in the area of organometallic chemistry. Indeed, organometallic chemistry is a very interesting and growing field. It has a lot of opportunities and a lot of big problems are being addressed using uh, the skills that are present or toolbox that are present for organometallic chemistry. So this course sort of highlights some of these useful aspects of organometallic chemistry so as to arouse interest in this area. I hope that you have found this course interesting the way I just mentioned. And in this live session, we are going to be taking up any questions or comments that you have. So again, I mentioned that please send us your questions through this text box and we will answer them as we receive them. So again, request students who are attending this session to text us your queries or doubts and we'll answer them as I receive them. Once again, welcome to this second live interactive session for this NPTEL course, Transition Metal Organometallic Chemistry, Advanced Transition Metal Organometallic Chemistry. So I request the students who have joined in this live session to send us your queries by texting them. You must have attended, by and large, the significant portion of this course, or almost towards the end right now. And this is a nice opportunity to clear your doubts uh, uh, and also to resolve your queries prior to the start of the exam, which is going to happen from next week. So in this session, we are going to be answering questions, if anything, that you may have at your end, and we'll clear them. And hence, I request you to text us your comment, questions, and queries regarding the course. Nobody is logged in on the people. Wait for another week. So you wait for another for 5 minutes, 5-15 minutes, because I don't think there is a mistake. Oh, yes, Somaranjan. Uh, uh, please explain shop process. Yes, this shop is a very important as well as significant organometallic discovery, and this process was sort of this process was evolved and discovered by industry at the requirement or need of the industry. So in particular, then as the name suggests, it is shell higher olefin process. So uh, uh, in this process, they were trying to make or form olefin oligomers. Now, the genesis of this problem is that uh, uh, like the industry was like industry at that point of time in 1960s or 70s, they were making surfactants for which they needed long chain fatty acids. Now, the kind of fatty acids that they were using, that was creating environmental problem uh, uh, at that point in around the river basin. So they needed to make fatty acids of not very long chain of like C4 to C18 fragments. So that was something which was idle as far as their requirement was. And for that, what they needed is of the several available technologies, one approach was to make alpha olefin of that length. And the problem at that point of time was that if you use early transition metal like titanium zirconium, electron deficient metal, and take ethylene, then they are going to make polyolefin, which are extremely long in chain length. So they become polymer. And then they were of not much use towards making these fatty acids. So what Shell did it, Shell found that if you stay away from early transition metal like titanium, zirconium, which were the catalyst used for making polyolefin polymers using Ziegler-Natta system, and use instead electron-rich late transition metal like nickel. In this case, they found that they could make alpha olefins of C18, C20 fragments. And then that was sort of the discovery which started this swap process. So they found a nickel catalyst. This nickel homogeneous catalyst is a nickel phosphine catalyst, which was structurally characterized and then used to make alpha olefins. Then they the swap process consists of three processes. First is the alpha olefin formation. The second is olefin rearrangement from alpha olefin to they make internal olefins, and then they use olefin metathesis to bring them into smaller ratio. So in that way, by using all the three processes, one is alpha olefin synthesis using the nickel catalyst, which I just spoke about. Then isomerization reactions, whereby they make the internal olefins, and olefin metathesis. They could get alpha olefins of the fractions or fragments they would require, which was required for making the desired fatty acids. So in that way, this was a process which was developed at the industry and by the industry, because to meet its need and also to avoid environmental hazard, that they used late transition metal like nickel to make alpha olefins, which are oligomer in nature, not of higher chain length, and then coupled it with two other famous reactions. One is olefin isomerization, followed by olefin metathesis, and in that way they got the fraction they needed for making the desired fatty acid. So this swap process was developed by the industry, and that industry name, the company of the name is Shell. Shell. So so it is in that name also it is called, it is Shell higher olefin oligomerization process, and that is a SHOP. Now this has been discussed in details in the class lecture, I believe, and you should refer to the lecture as well as the reference book I have referred to for more detailed study on that. Does it answer your query or clear your doubt? Okay. Is oh yeah. What is okay? Now, why they use MAO? The MAO is methyl aluminum oxide. So it is a methyl aluminum partially hydrated. So you have partial hydrolysis of trimethyl aluminum. The structure of MAO is still unknown, and it's a polymeric structure, and it is methyl aluminum, like any aluminum alkyl compound, is extremely pyrophoric and difficult to handle, and so is MAO. Now, MAO was used for titanium halide complexes to make the to methylate the chlorides or the halides and to make the titanium alkyls. And then the titanium alkyl are the originate propagating or the pre-catalyst for carrying out the polymerization reaction. So purpose of MAO was mainly to alkylate the titanium halide to make it titanium methyl. And then once that is formed, the second purpose, let's say titanium halide has been converted to titanium methyl, the next role of MAO is to abstract that methyl and to make the titanium vacant cationic coordination site where the olefin will come and bind. So the like if you look at deeply, then there is twofold roles of MAO. Twofold roles. One is the alkylation of the halide to make titanium alkyl, and second is the abstraction of the halide to make to create a cationic vacant site. Trimethyl aluminum or any aluminum alkyl are trivalent electron deficient species, so they would also abstract another alkyl species and become Al R4 minus. So the role of MAO is twofold. One is to alkylate, second is to the abstraction of the alkylated metal complex. Is this clear to you? Please explain the important points to be organometallic complexes via base mediated reaction. See, the things to be kept in mind while making organometallic compound is primarily to preserve the reactivity of the compound which is so formed. So organometallic compound so synthesized. So the precautions which are taken are one, exclusion of air and moisture. So you have to keep your reaction vessel free from moisture and air. And you should be able to carry out the manipulation in inert atmosphere or exclusively dinitrogen atmosphere. Now, why you have to keep away your organometallic compound from these two things, air and moisture? Now, air means air is 80% nitrogen and 20% oxygen. So it's not that you have to keep your organometallic compound away from dinitrogen. Dinitrogen is inert. By air, it means that you have to keep your compound away from oxygen of the air. The oxygen component, which is only 20% component of the air, and moisture. Moisture is even more lesser amount. It's not even like 20%. It's much way too less. Now, organometallic compound gets hydrolyzed if it reacts with the water of moisture. So basically, you have to stay away from water and oxygen. With water, what does it do? With water, it hydrolyzes and makes metal hydroxide. And that reaction is extremely fast to the extent sometimes it is pyrophoric. Then what does it do with oxygen? It also reacts, and sometimes oxygen oxidizes and make metal oxos or other oxidized compounds. So one has to in principle, whether you do it in base or in absence of base or with base or anything, you have to maintain a anaerobic environment while you do the manipulation. Now, having said that, not all organometallic compounds are highly reactive. Uh, the reactivity pattern of transition metal organometallics vary. For example, magnesium alkyls, Grignard is very reactive. On the other hand, alkyl tin is not that reactive. Hmm. So there are plenty of examples in which some compound you cannot handle in air, and some compounds are organometallic compounds are also stable in air. So the reactivity vary, and depending on which metal and which functionality you're using, you have to take precaution based on that. So the rule of thumb is that early transition metal organometallics are reactive, alkali metal organometallics are reactive, whereas main group organometallics are not that reactive, and late transition metal organometallics are not very reactive. Having said that, one needs to take enough precaution for any of these anyway. So the main experimental challenge is to maintain a anaerobic, air-free, air and moisture-free environment while carrying out various manipulation for the synthesis. And after synthesizing it, you have to have air-free anaerobic environment where you can store the compound. For example, you have made the compound under extremely rigorous air and moisture-free condition, but later if you want to record the NMR in a deuterated solvent, let's say CDCl3, and if the CDCl3 contains trace amount of water, then you will not then your compound will get hydrolyzed in the NMR tube. So you will not know whether you have made the compound or not. So all aspects of the manipulation has to be extremely air have to be performed under extreme rigorous conditions in terms of keeping it air and moisture free. Is that clear? Please send us your comments and queries, and in this last interactive session, I'd be happy to answer them. While trying to synthesize a zinc complex with an organic ligand having nitrogen and sulfur donor sites, I am not successful. I am a PhD scholar. Okay, let me put it to you that all of us will not succeed in one attempt or two attempt. So you and you know the adage that failure is the pillar of success is very much applicable for an organometallic chemist. We learn through failures. So once we fail, we try to understand how we fail or what is the reason behind our failure. Now, if the reason is clear, or if you can investigate why we failed, then the corrective measures accordingly can be taken, and then one can be successful in overcoming it. Now, in your case, you have to see why the reaction did not succeed. There may be so many possibilities, and you have to identify each of these, or you have to investigate each of these to either rule in or rule out, and then finally whatever is ruled in, that is the essence or thesis of your investigation. Now, as I said, that let's say if you're doing an organometallic reaction, but if the solvent is not dry or dry enough uh, to meet the requirement of the reaction, then you will never get the product. You will never get, because there will be trace amount of water that will kill the product. Even it's not that the reaction is not happening. The reaction is happening and you're making the compound, but then the water in the solvent is killing the compound after it is so formed. So if that be the case, then you have to make your solvent extremely dry. Now, there are methods to find out to what degree of dryness the solvent has been dried. And there are several like benzophenone, sodium, and the color of the sodium will tell you prior to distilling your solvent to what degree it has dried. Now, if a reaction demands for extremely dry solvent, and if you use a solvent which is wet solvent, then obviously the reaction will not proceed. And this is what you have to find out through every attempts and take corrective measures. For example, you try the same reaction with a rigorously dried solvent. Then you see whether your reaction is proceeding or not. Sometimes maybe you have used a dried solvent, the reaction still doesn't go. So then you have to see whether you have to monitor the extent of the reaction with time. Maybe you need longer time, maybe you need higher temperature, maybe you need one reagent in excess to drive the reaction forward. So all of this you will have to investigate analytically. It's not that you cannot investigate by looking at the color or looking at it and thinking or feeling I have an intuition that reaction is proceeding. Your intuition most likely is incorrect. I have a feeling that color changed from red to yellow. Color doesn't mean nothing. You have to quantitatively or semi-quantitatively analyze. For example, take a reaction aliquot, run a NMR, and see how much of the reactant is left, how much of the product is formed. It has to be a quantitative analysis. And then let's say you run an NMR and you see that 30% of the product is formed, 70% is still the reactant. Then don't just work up the reaction at that point of time. Let the reaction proceed for another 6 hours. Then monitor it again. Take an aliquot, run an NMR and see. Now you may find that 70% of the reaction has converted to product, 30% is still the reactant. Again, just because don't get excited and start working up the reactant. Again, let the reaction proceed for another significant amount of time. Again, monitor. Now, when you see that while monitoring, you see that about 80, 90, 95% of the reaction has been converted to product. At that time, attempt your workup. If you attempt to work up at that point of time when majority of the mixture is the product in the mixture, then it's easy to isolate the product pure, because impurity is just the reactant at this point of time. On the other hand, if you try to isolate your product when the reactant is the major product and product itself is in minority, then you'll have to really struggle hard. You have to struggle hard and you have to have good amount of separation skills to isolate your product pure. So analysis is very important. Yeah, you don't have to blindly stop the reaction after 3 hours, 4 hours. Stop it when you are sure, for sure, know how much of the product is formed. So there are like this kind of analysis I just mentioned. No, such kind of thing has to be done at every stage and every day. Then some reaction will happen. On an average, failure is lot in organometallic chemistry. I can tell you some statistics in my lab. For example, if a student work on a particular project and if the project has 7 or 8 reactions from ligand synthesis all the way to metallation, 7 or 8 steps, sequential steps. So they may have to do 500 reactions in that direction to have 7-step pure and clean. so that they can write a paper. So 500 attempts can clean up 5 to 7 good reactions that can fetch one paper. So that means that 495 times the student might have failed, like you, and succeeded maybe 5 times or 10 times. So it's part of the deal, part of being a PhD. Okay, LLDP, linear low density polyethylene, high density, tell us about. Acha, these are all there in the lecture. Depending the olefins are, please refer to your lecture. The olefins are graded based on the branching, their melting point, and all of this has been discussed in details in the lecture. There is a chart also, I believe, in transparency. The classifications. Okay. This is huh? in the other course, but this is there in this. For what my TAs are telling me that this LLLDP and HDP is not in the purview or syllabus of this particular course. That is in advanced transition metal organometallic chemistry, but you should know that see, when you make polyethylene is a polymer. Now polyethylene, this polymer that you make, they have different types of properties. They have different types. Some are hard, some are brittle, and each of these property can give rise to different applications. Some can be made to make tubes. Some are made to make something which can bend. And if you look at the composition, they are all polyethylene. So what makes them different? The thing which makes them different is their branching, their linearity, their melting temperature, glass transition temperature. And what it so happen is, depending on the method of polymerization or transition metal you use to polymerize, you will end up getting different kinds of polymer. And that has been studied extremely in detail, and so is Philip process, Ziegler-Natta, and other processes that you're referring to. So each of these would give you a certain type of polymer, and they are characterized by their molecular weight, by their physical properties, and that can be correlated with the degree of branching, degree of cross-linking, so on and so forth. So this is discussed in detail in that NPTEL Advanced Organometallic course, and probably not in this course. What I'm saying. Was this helpful? Okay, again, if you have any further questions, please text us. I'll be happy to answer them. Once again, thank you for joining this live interactive session for this course, Advanced Transition Metal Organometallic Chemistry. I request the students who have enrolled in the course and who are present in today's interactive session to send us your comments and queries. This probably is the last interactive session before your exam commences from next week. So this is a nice opportunity to get all your doubts cleared prior to you taking the final exam. It's changing the solvent from butanediol to N-hexane in ethylene oligomerization process in the step of results. What should be the answer? What is it? Is so this answer should be shared in the assignment also, no? Huh? What I am told that this question is not for this particular course. I think you are sending assignments of another course. Yeah, it is what the TAs are telling me uh, that this assignment does not belong to these folks. Anyway, for the answer to that will also be shared in the previous course as well. Mukesh, I'm in a class right now. Can I call you in 2 minutes? I'm in a class. No problem. Bye. The formation of high molecular weight linear poly. This is not this class, no? Somarajan, I request you to stick to this course's assignment. And for the other course, there was a live interactive session because there may be people or students for this interactive session who may have questions with regard to this particular course. See, the point is this, no? The idea is that it says uh, if you have a solvent with a protic solvent, it says diol, no? Versus you have a non-protic solvent, which is hexane. So the catalyst will live longer. The active species will live longer. If the catalyst live longer, that means your polymer will take for a long period of time. If the polymerization process takes for a longer period of time, you will make long molecular weight polymer. It's as simple as that. Whereas if you take a solvent, let's say water, if you do polymerization in water, you may not even get oligomer also. Because immediately the catalyst which would be formed that will react with the oxygen, the proton of water OH and get killed, poisoned. So that's why most of the olefin polymerization reactions are carried out either in non-protic solvents like toluene or hexane, which does not have anything to protonate. And also some high temperature is required, because many times polymerization will occur at 70, 80, 100 degrees centigrade. So you cannot take also let's say a non-protic low boiling solvent. Thank you. Very something. Actually, things this both are there back to back. No? So I don't realize where that one starts and where this one ends. Okay. Again, once again, I thank you for being in the live session. We have had some very interesting questions, and I request you to send us your queries. We'll answer them, and this is a good opportunity for you to interact and get your doubts cleared. This being the last interactive session. Hmm. And from next week, you're going to be having your final exam. I wish you all the best. I hope you have gathered some knowledge, and also your view about this field of organometallic chemistry uh, in becomes more matured. You have obtained a matured perspective of the field, and that you find the field exciting. So we'll wait for some more time before we sign off for today. Please do send us your comments or questions if you have any. So once again, I request you to send your queries. We'll wait for another couple of minutes, and if there is no further questions, then we will close the session for today. I wish you all the best for the final exam. Uh, Hope you have had a good preparation, and I hope you have enjoyed the course. That is the most important of all, immaterial of how you find the exam. And if this course succeeds in arousing your interest in the area, then I think the course would have served its own purpose. So with that, I thank you once again for joining today's live session. We are going to close today's session call right now, and I wish you all the best for your final exam in the coming week.